computer. That's on the start the record. Okay. So good morning, everyone. Welcome to the class. Last time we talked a little bit about the structure and the introduction to the structures around the university or on campus, I should say. So today I would like to begin with the introduction to the load first. Generally, we need structure to support the load, right? I think we probably mentioned that last time. If you don't have such thing as a load, we don't need the structure to support it. So maybe, for example, in the old days when people lived in the cave, a cave is a natural structure. So people at that time, they just went out. Okay, they discovered the cave and it's strong enough, so they went in and lived in the cave. So now we need more freedom to go and live anywhere. We start building a house. And then you realize that in order to have a safe house, the structure that forms a house must be strong enough to support something. And when life gets more complicated, when you build a structure, now it has to be, based on the law. So you'd say, this is part of the law where, as an engineer, you must be aware of the fact that you need to design your structure to be able to support the external load. Now, generally, the load that you see listed here, this is from the class note, the handout that I gave you. If you look at the chapter 1, I begin the chapter by talking about the load. So, okay, generally, this is the law. Okay, so why do we have the law? You must be aware by now that in order to be an engineer, you need to have a license. This is a profession where license is required, which means you are doing something that you have to be qualified for. Not everyone can become an engineer unless they are qualified. And the symbol of that qualification is your license. So when you have the license, you must be aware of the law as well, okay? So generally, when you want to build something, you want to build structure, you need to know that there are laws telling you that, okay, your structure must be able to support the date load. Do you know what date load is? I don't know if I have the definition in the next page. I don't have, so let's talk about that a little bit. A date load, by definition, is the load that magnitude doesn't change against time. So you can say magnitude is constant. Okay. Can you give me an example of the load where its magnitude is rather constant? Anyone?
Cell weight of material.
Oh, that's good. It's a self weight. So Nakarin, you're enjoying the class now. You participate. I hope that the rest of you do the same thing. Yes, it's the weight of your structure, weight of your floor, the weight of your stuff that you use, furniture.
Furniture, right?
Furniture is tricky because, let me continue to talk because there is furniture that hardly moves, right? And there's furniture that you can move around. Because when we talk about the next type of load, the live load, what is different from date load is that the magnitude of the live load changes all the time. Like us, for example. Now I am in the dining room. I can leave the dining room. And when I leave, the dining room has no load from me, right? So furniture, if you consider something movable like sofa or dining table, coffee table, that is actually part of the live load, But if you're dealing with something super heavy, like some safe that they use to hold like the files and stuff like that, and it's supremely heavy, in some countries, the law would say, okay, you can treat that as a dead load, stuff like that. Now, you need to study the law pertinent to where you're going to build your structure. And in the end, it is you who are going to make the final judgment, what kind of load you are going to use on your structure, what you're dealing with. For example, if you are going to design a warehouse, okay, you know what a warehouse is? I think you do. So the law would say, if you're going to build a warehouse, the minimum live load that you need to use is perhaps 400 kilogram force per square meter. I don't remember exactly what it is, but you as an engineer, you must know what that warehouse is going to contain in the future. Because the law say minimum 400, doesn't mean that you are going to use 400. But whatever you use, the minimum number you should use is going to be 400. But if you as an engineer are aware of the fact that, okay, the owner wants to store maybe rice or books or, you know, some steel billet, it's going to be supremely heavy. So 400 would not be enough. You as an engineer must find out what is actually the load or the goods that they want to store in the warehouse and make the sound judgment of what live load you are going to use. The law say one thing, and you cannot always say, hey, I follow the law, I use 400. If the building falls down, it's not my fault. But it is your responsibility nonetheless. Okay? Now, generally, these two loads, we can say it's, you know, it's a vertical load. This is vertical. Or you can say it's caused by gravity. So some would say it's a gravity load. Okay. Now there are some other loads where, you know, they don't come in the vertical direction, as we mentioned the last time. So the wind load, the law would say if your building is tall beyond some certain level, you need to make sure that your building will be able to withstand the wind load. And the way you can calculate the wind load is pretty much based on many standards, which the law would, you know, refer to. So you need to be able to calculate the wind load acting on your structure based on the standard pertaining to the law. Okay, an earthquake is the same. This is the horizontal load abided by the law as well. Okay, so you as engineer must figure this out. And there are some other loads where you face in the future, like for example, pre-stressing force. This is the force that engineer induce to the structure to help increase the capacity of the structure, you know. So yes, the load carrying capacity of the structure will increase due to this load, but the load is a load. So you must make sure that before your structure, you know, is getting stronger, it must be able to withstand this load as well. And the earth pressure is another form of the horizontal load. Say horizontal here. And in some other places, there will be some special load like flood or snow. You don't have it here. Snow load is gravity load. And many big buildings in the US, you know, collapse because of the snow load. Because even though they designed the buildings for the snow, but when the like maybe 100-year snow hit the town, you know, the load would be by far worse than the engineer thought it would be. So, you know, it happened. And somewhere you can have like extra load where you have never heard before, like blast load. In some buildings, it will require you to design your building to withstand the blast from bombs. This is serious. And plane crash. Have you heard of it? Tall buildings in the US are required to design to withstand the plane crash. So if you can recall, this is a sad thing to say, but it's true. World Trade Center building, WTC, that collapsed. When the plane flew into the buildings, those two towers, you see the buildings did not collapse because they were designed to withstand the plane crash. And so they did. But the main cause for the collapse was the fire. Because they could not put out the fire that was burning so high up. That's why the New York firemen, they just rushed up, and then they couldn't get there in time because it was just so high, you know? So it's just a sad thing. Fire is another thing. So, you know, as engineers, you need to figure out all kinds of load that your structure needs to withstand. Okay, no excuses. And you will see why when you sum the load incorrectly in this class, I cannot let you go to the next level. Because this is where the most important thing is, the load. If you miss the load, it means that you are going to design or build the structure that is perhaps not as strong as it should be. Because you miss the load. You may miss some type of load. You may miss, you know, some load from the structure, so and so. So this is the most important step, especially when you use computer program, because the computer program will not tell you what kind of load you should put on it, correct? You must be aware of that by yourself. No matter how smart your computer is, the criteria on the load that you shall put on your structure is totally up to you, not up to the computer. And one more thing that you need to learn from here, but it's not the point of this class, but I will make you aware of that. What is what we call, I'm running out of space here, but I think I can just go up here. It's load combination. Because in the real world, you would not say that the maximum date load, maximum live load, maximum wind load, maximum snow load, maximum earthquake, they're going to happen at the same time, right? That'd be crazy to think of yourself, hey, I'm in the building where the hurricane is coming and the earthquake is also coming at the same time. And then the building is filled with people. What kind of building is filled with people when the hurricane and earthquake are coming at the same time, plus the flood and the snow? So we cannot put everything on the structure and design the structure so that it could withstand all kinds of load coming all together at once. It's going to be extremely expensive, and you're going to end up with the size of the structure so big that you cannot live in your building anymore. So we have to be sensible and think about what kind of load that would happen, that can happen at the same time. That consideration is what we call the load combination. Okay. Some law will give you the suggestions on the load combination. Some will be pretty loose on it. So you as an engineer need to study this very thoroughly and understand what's going to happen. For example, the maximum date load and live load can occur at the same time. Okay. So it's the most basic one that you need to cover. Sometimes when the maximum wind load occurs, at that time, the live load may not be as much. So the combination of date load plus live load plus wind load, you don't go with the full live load. Things like that. Or in some cases, you know, people evacuate before the earthquake comes. So it's a date load plus earthquake. And you need to study and try to cover every load combination possible and pick the worst case scenario out of your analysis and make sure that your building will withstand the worst case scenario. Okay, so that's a load side of thing. Any question on the load? Quiet means we are crystal clear, right? So now when we have the load, we need to have the structure. Okay, so let me try to use something like this. So when you have the load, you put the load on the structure, okay? So now your structure is carrying the load. Now what you need to do is to perform structure analysis. You know, analysis is singular. If you have so many analyses, it becomes analyses. So that's a plural form of analysis. You just change an S to an E and you pronounce analyses. That's plural form, okay? And once you perform the structure analysis or analyses, you will get the internal forces of your structure. Sorry, you should, yeah, right, interforce, okay. Internal forces or stress or strain and so on. So now when you have the force and stress and strain, this is when you going to compare what's going to happen to your strength of material, right? If your material has a strength above the stress that occurs in the structure, that means it's going to survive, right? But if the stress that occurs exceeds the strength of your material, that means you're probably going to have the collapse on hand. That's why you study the strength of materials, to be able to relate the stress caused by the external load to the strength of the material that you use. Okay. Now, generally, the structure analysis here, you know, is taught to you by the subject we call statics. But static is just like it gives you the basic idea of how the equilibrium works. But when your structure becomes more complicated, for example, I'm going to show you. Let's say if you have the floor, okay, and if I have two beams like this, okay, I'm gonna try to draw one beam, okay. You know, the wonderful thing of having the online class is you guys don't need to draw this if you don't want to, but in the real lecture, you guys will need to draw these pictures yourselves, and I'm gonna mock you guys a little bit of your poor drawing qualities and so and so. But now I'm the only one who draws, so you can, you know, mock me behind my back or just mock me now. But I draw pretty okay. So let's say if you have two beams, you put the let me try to use the different colors, see if it helps. This is another beam, but I'm not gonna draw it. But let me, if I put the floor on this, right, floor will have like each piece like that. Okay, so you see the floor itself is a simple beam. That means half the load will go onto the beam on the left, half this piece, and then another half will go onto the right. Half of this piece will go on to the left as well. Okay, and then another half will go to the right. Half of this goes to the left. Half of this goes to the left, and so and so. So that means this becomes the load that acts on the beam on the left. Okay, and say if I put the columns here underneath this beam. Okay, this beam would have the support and it's a one span. So you can say that this is your simple beam. And you already have the blue, pink columns as the support. So from this real picture, I can easily draw the free body diagram of this beam. So it's going to look like this, right? And the load acting on this beam would be this blue floor. Okay, coming on to this. Are you guys with me? Excuse me, it's an ant on my computer. It goes. It cannot withstand the wind load, you see. So, okay. So the pink one here, these columns will provide the support. So I can paint this pink so that you know the columns are these two supports for the beam. And the pink, the blue one, this is the weight of the floor plus the beam self-weight. Okay? So that's a simple structure with just two beams. But in the real world, I'm not going to have just this area for my building, right? So I could probably have more beams going on like this. And then I have more floor coming in. I put the floor on it again. Okay? And that means now this guy, you know, this beam would have to support the beam in the middle here. Would have to support half the floor from the left and then half the floor from the right. Okay, so for the sake of you know, clarity, let's give this beam a name B1. And this guy in the middle, I'm going to call him B2. And B2 would have to carry the floor twice larger than B1, okay? Because now B2 would have to carry the floor from this point on up to this point. Any question, folks? No. So let's say, you know, I kind of don't want to have so many columns because it's just going to get in my way. So let's say I am going to turn this picture into a top view picture. So let's move on to the next page. So I'm going to draw the floor plan now. Okay. So let's say this is my B1. That's my B1. Okay. And then that's going to be my column. Looks okay. And this is my B2. But perhaps I don't have one B2. I have like plenty more. Okay. And then I say, let's have more columns. I cannot say this, generally it's architects saying, you know. So let's say they have more columns here. So, and then you have a series of B2 coming in like this. Oh, handwriting is so ugly. Let's do it again. That's B2. Okay, so B2s don't go straight into the columns. So we're gonna need to provide the support for B2, right? So that's when we're gonna have to have like more beams here to support B2. Okay, you guys stay with me, I hope. So let's come back to this picture. You see B2, you know, is supporting the light blue floor here. And you can see the direction of the floor is that, you know, it goes on to B1 and B2. So we use this symbol to indicate that we want to place the floor onto B1 and B2. So when you look at your floor plan, you will see this symbol. Okay? So when you see this symbol, you will realize that the floor is placed on B1 and B2s. Okay? Small pieces like this, a lot of them. Okay? So the one piece of this blue floor, you can see it from this one. I don't know why I removed this. So let's one second. Okay, this one. So let me try to expand that a little bit. That's a piece of the blue one, you see? They make it a small piece of the floor, and in Thailand we call this plank. A plank is the smallest one, or if it gets bigger, it's called the hollow core. Now these two are made of concrete. You can also have the one made of steel that is called metal deck. Okay, but again, you can see the direction that the floor is placed on the structure. And in this case, we use this symbol. So this red beam will support half of this plank and then another half from this. Okay. Just to make it better. Okay. And yeah, that's the direction of how we place the floor. So as I say, this is the tributary width that your beam must be responsible for. And if we come back to this one, yep, you guess this is the tributary width. The same one shown in the picture. Okay, and generally you would see that we call this, there's so many names of it. This beam is called, how do I do it? Okay, let's move to on the left because I want to use this space again. This is called the secondary beam. Some will say it's a filler beam. And some will say it's a joist. You know, in a system of Thai houses back there, you know, a long time ago, where we use wood, we use this kind of system, but we don't call this a secondary beam. We call it tong. Na? Have you heard of that word? Tong, not trong. Na? Tong. So it's a joist. Tong is a joist, and there's so many names for it. But as you can see from this floor plan, the B2s need support. And in this case, we are going to provide the support for B2 by using this beam called B3. Right? And if you look at B2 itself, the B2 is pretty similar to B1. But it's going to carry more weight or more load from the floor. Okay. Let's say it would be nice to work with some numbers. I know you guys need numbers. So let's say our tributary width here is 4 meters. Please notice that because the tributary width is always half the distance between each secondary beam. So if you place them equally, the tributary width is generally equal to the spacing of your secondary beam, right? So let's say if the spacing between B2s, oh, I want to be more distinctive. Okay, let's use this one. Let's say the spacing here is 4 meters. Chances are the tributary width is going to be 4 meters as well, unless somebody's crazy and messing up the spacing, okay? All right, so folks, this load is coming from the floor based on the tributary width of 4 meters, and then plus the self weight of the beam. Right? Now let's come back and take a look at the our B1 a little bit. Let's to reduce our confusion. This is B2. Okay, and let's look at B1. This is one. It's a little bit low. But B1, you see now that we have the numbers. The B1 is the floor, the tributary width of the floor of B1. I'm trying to use the same color. So it's going to be, it's fine. Floor width, the width, because it's a beam on the edge. So the tributary width is 2 meters, correct? It is only responsible for half of the floor on the edge. Meanwhile, B2 will have to be responsible for 4 meters. So now let's take a look at the beam number B3. When I draw B3, now B3 will be the one who has to support B2, correct? So yes, that will be reactions from B2. These will be the reaction from B2. And what else are we missing? We are also missing the weight of the beam B3 itself. So that's a free body diagram of beam B3. So up until now, is there any question? Hello?
No, ka.
No, ka. Thank you, ka. So let me expand this a little bit, because generally this one bay will not be enough to form a building. Okay, so generally this is not the only thing you're gonna have. You're gonna have more. So let me try to again use a different color so that you can feel the structure. Right? Let's just use the gray one. Okay. Generally, it will go on and on and on. Oh no, it's not straight enough. Okay, and it can go on to the right like this, and it can go on, down here as well. So, generally when you look at B3 now, many times B3, it's not going to be just one beam like this anymore. As you can see that you could probably have more than one B3, they go on and on and on like this. So when that's the case, your structure becomes more complicated, because instead of having just 1B3 now, you are going to have, let's use a new page. Okay. Before that, you sort of have like 1B3 like this. And in the real world, they don't build simple beam and put together, you know, because you are going to learn in a short future that a simple beam is not a very strong structure. So when you're beginning to have more than one beam, that's 1B3. And then you have more. And then you have more. Let's say we stop at 3, okay? Now you're gonna face the structure where for the first time, you have a lot of reactions more than you can solve. Okay? So let's say, this is just the introduction, okay? So don't get too downbeat about this. So you now have this reaction, this reaction, this reaction, this reaction, then that reaction. So how many reactions we have here? I guess we all can count, right? Why am I asking? I'm just asking for your participation. So we have here 5 reactions. Okay. How many equilibrium equations do you have? Oh, yeah.
3 ครับ
Oh, thank you. We always have 3 equilibrium equations, right? We always do. We're not going to have more than that. So when we have only 3 equilibrium equations, meaning we are now 2 shorts. We are now 2 equations short of what we need, right? Because in the typical world, when you have 5 unknowns, your reactions are your first unknowns you need to solve, right? So when we have 5 reactions, I can easily call them unknowns. So in this case, we have 5 unknowns. We have 5 unknowns. You can see yeah. But we have 3 equations. So we need two more equations so that we can solve 5 unknowns, correct? It's that simple. So the difference between this two more needed, 2 more equations, needed. So when you have the numbers of unknowns more than the numbers of equations, we call this situation indeterminate. And to be absolutely correct on the name, it's actually officially called statically indeterminate structure. Sorry. Statically indeterminate structures. And because you need to have 2 more equations, these 2 represent the degree of redundancy. Your 2 equations short, it means the structure has 2 degrees of redundancy. You need to find 2 more equations equal to the degree of redundancy before you can solve this structure. Okay, so this is the example of how the structure can get complicated so that you need more tricks in your sleeves to solve the structure, because your sigma fx, sigma fy, and sigma moment will no longer be sufficient. So in the beginning of the class, we just give you how, the load can be transferred onto your structure, and they will get on to this kind of stuff, you know, when you need to be able to analyze the structure more complicated with the new method. Okay. And ladies and gentlemen, I can tell you right now that in the real world, you can hardly find simple beams or cantilever beams. Most of the time, you would face a structure like this, you know, structure with more unknowns than you can solve for. And we call this the indeterminate structure. And I should give you also the name that this beam is the continuous beam. Because it has more than one beam put together to create the continuous form. And you need to analyze them at the same time. Okay, I am running 3 minutes into the break. I would like to talk to you more into the system of the structure, but I don't want to stop short in the middle of the break. So we have 3 minutes. Is there any question?
What is tributary wind?
Can you say that again? I don't quite understand you.
I think what should I say?
Okay. We can wait. I can wait. Just be calm. Okay. Nobody's English is, you know.
Okay. Tributary winds. Tributary winds.
Oh, tributary width.
Yes.
You know, the trick of the English is that you need to find the right place to stress. So it tributary. If you forget about the 3 and 3, you know, you just build. You stress the word build very strongly. Tributary width. Okay. So the tributary width is the width that your beam must be responsible for in terms of carrying the floor or the load. Okay, so let's come back to this picture. Okay, you see this is the real beam, right? You see the red beam here. This is your red beam. This red beam will be responsible for half the floor on the left. You see this one? You okay? Are you with me? I'm
yes.
Ending. Yeah. So because half of the floor, the other half would be carried by this beam, right? You agree?
Yes.
I don't paint the other half of the floor. So this half will be carried by this beam. And likewise, we have the floor on the opposite side, on this side, which is this one. So I'm painting it again. Half of this, again, will be carried by this red beam, right?
Yeah.
Okay, so that means this red beam is carrying half the floor on the left side and another half on the right. So it's half on the left and it's half on the right. So the width of the one half on the left and then the width of one half on the right, when you combine them, it becomes the tributary width. See? Actually, it's this side and then it's that side. When you add them up, it becomes the width of the floor that your beam has to carry. So when you add this up with that, it becomes the whole width here. We call that tributary width.
So, okay. Thank you.
No. I'm very happy that you asked me. Please don't feel that if you don't get it, if you need one more explanation, please tell me. The point of you guys being in the class is to make sure that you understand the content. I'm not going to embarrass anyone, okay? You're here because you want to be an engineer. So can we always consider tributary width of the beam by the width of the slab? You know, it's pretty tricky and the word width itself, because right now, the width, if you talk about the width of the slab, I'm sorry if this confused you, but let me try to explain it, okay? The slab itself. Hey, come on. The slab itself comes in the shape like this. I'm trying to draw in the same direction. Looks like a mess. Let's try again. Okay. The slab comes in like this. But it comes in many pieces, you know. So when we talk about the width of the slab, it's actually this width. You know what I mean? So the width of one piece of the slab, but the floor is formed by putting so many slabs together. So when we talk about the tributary width, it's actually half the length of the slab. It becomes the width of, you know, the floor that the beam has to support, not the width of this one piece as a slab. So when we talk about tributary width, it's actually this. Half the length of the slab will become the width that the beam has to support, right? Let me try to demonstrate something. Let's say, can you see this iPad? Too big. Okay. If I support this iPad by my two hands, like this, the weight on the left of this iPad will go to this hand, and then the weight of the other half of this iPad will go to my right hand here. Okay, but the width of the iPad is this, right? We don't talk about the width of the iPad itself, but we now talk about the width that my hands need to carry. It becomes this width, or half the length of the iPad. So my right hand is supporting the half length of this iPad, right? And let's say if I have another slab on this side, my right hand would need to carry another half of that. So half the length of this and then another half on the right will become the tributary width that my right hand need to be able to support. Is that better? You know, and it takes a little getting used to, I should say. And the most common mistakes that students make is that they use the wrong tributary width because they got confused with the spacing. And, you know, I can say I'm cruel, you know, you can ask the senior, but generally when we talk about the structure, like this, for example, we're going to do this. When you look at the floor plan, they don't give you the tributary width, because that's how the structural drawings are made. Because people need structural drawings to construct, for construction, right? So they don't create the drawings for ease of calculation, because they need those drawings for real purposes of construction. So they always tell you stuff like that, you know, they tell you the spacing so that people will know how to put all the secondary beams in place with the spacing. But you need to know that this spacing will can be turned into the tributary width of the beam. And, you know, some students will get a little bit confused and they mess up the tributary width. And when you mess up the tributary width, that means you put the wrong load on the beam, the rest of your work becomes garbage instantly. You know what I mean? So does that help clear the tributary width issue? You know, I'm gonna stop the record for now. Let's say so that you are more comfortable in asking the question.